This is really from chapter 8. It's looking at a formula. So if you had to write a formula to build this wheel, you are giving directions to somebody else to tell them how to build it. What is our formula for this wheel? Any ideas? Count the spokes. We're not looking for the area of the wheel. Not a bad idea. So we could count the number of spokes. I'm going to guess that there's 32. Is that it? There's just 32 spokes in the wheel? Okay, we got a rim. How many rims are there? One. Okay. Could get more nitpicky in it. What else is in there? We got a tire. I was waiting for the hub to come in there too. We have a hub. Okay, we've got a lot of individual components within that. What we're doing within chemistry is simplifying that down into an individual symbol. What would be a nice symbol for spokes? S. How do I know there's 32 of them? Okay. We can say in the lower right-hand corner, we'll put a number that corresponds to how many of those individual things there are. It's a symbol for our rims. Very creative here. Lower right-hand corner, we have a 1, okay, which we get tired of writing, so we can imply the 1 just by writing it. Tire. Okay. To be more creative with the exact order of those symbols, which is ultimately what chemistry goes through and does, is put a more structured order behind it. But that's all we're doing with a formula. Okay, we're counting up the pieces that went into it. How many of those individual pieces build this wheel? It becomes trickier in chemistry because all of those individual particles are incredibly tiny and we can't see them. Okay, so we don't have a way to grasp a hold of those. Same idea is happening with an equation. Okay? Provide simple instructions to build a bicycle. And by simple, I mean we only have wheels and a frame. What would you need to do? We need 2 wheels. And how can we specify that we need 2 wheels? We need 2 wheels, and we need 1 frame. And now we have 1 bicycle. That's what our chemical formulas do, the exact same thing. But again, we can't see those particles, so it becomes trickier to work with. Okay. The other thing that you need to be aware of is that when we look at that equation, okay, that representation of how to build a bicycle, okay, only one of you offered a suggestion, and I appreciate that. But within that suggestion, it was 2 wheels. Did you say anything about mass? No, why not? What do you mean it doesn't ask for it? Think about the directions. Anybody put together furniture, IKEA furniture, anything like that? When you look at those directions, does it say this package comes with 50 grams of screws? No, it probably says there are 10 screws. Okay. How many of you have a balance that would weigh out 50 grams easily at home? One of you? Okay. What are the rest of you going to do when the package says 50 grams and it actually came with 40 grams? You would have no idea. You start to put it together. You assume all the pieces are there because you have no way of checking if everything is there. And you get to the end and you go, well, I can't put the door on the thing because I'm missing a screw. Okay. So the directions give us something that we can measure easily. What is that thing that we can measure easily? The number of a species, the quantity. Okay. Because in all those cases, what those manufacturers are assuming is that absolute worst case, you have the ability to count up to 20. Somebody process that one real quickly. How'd you count up to 20? Fingers and toes. Okay. You have an ability to count, okay, very quickly with your brain. You can do that. That's what our equation is doing. It's counting the number of molecules. Not the mass, it's counting them. That becomes problematic for us as chemists, because if we're going to go through and run a reaction, we need to know the mass of those particles. Why do we need to know the mass? Why do we have to do a mass? Why don't we just count it? We said counting was easy.
There are too many of them.
They're so tiny that to count out the individual particles, we can't do, because we can't see those particles. We can't grab a single atom or a single molecule and react it with another single atom or a single molecule. We end up having to do this on a much larger scale, where we're grabbing hundreds of thousands of molecules and hundreds of thousands of atoms, and we're putting them together and allowing them to do their work. Right? We then have to predict that. Because I can't count those particles, I have to have some other way of measuring them. That's where we bring in the balance, and we have to start weighing things. Right? So we need to be able to see what our equation tells us between numbers of species and now mass. Well, where do we find the information between mass and numbers of a species? That's what our periodic table gives us. You have these conversion factors. They are there. You just have to start finding them and using them frequently. Okay? Someone built 4 bikes. How many wheels and frames were used? Okay. This is fascinating. You guys are all doing this in your head. I didn't see anybody write anything down. We could write something down for this, because it's what we're asking you to do with chemistry. We have a formula, an equation that tells us 2 wheels plus 1 frame equals 1 bike. If I have 4 bikes, and I'm being asked for the number of wheels, how do I do that conversion? Well, bikes do not equal wheels. How do I convert between bikes and wheels? 2 wheels produces 1 bike. I now know that the number of wheels I needed to build this was 8. This is what the equation gives you. You're able to process this in your head only because you can see these particles. You can see a wheel. You can see a frame. You can see a bike. You're more aware of those. You have to now abstract beyond the visual and into this kind of nether realm where we can't actually see it. It's that abstract thought that makes chemistry difficult, because we're asking you to apply a concept that you are readily aware of, that you can process on your own, to something that you now are assuming works because you can't see it. Okay. And it turns out that assumption is incredibly valid, because we can go through and run calculations and run experiments, and we can predict and see that these equations are valid. That is the point behind looking at these larger formulas, or these larger equations. Okay. So let's make the question a little bit more challenging. Given 3 wheels and 2 frames, how many bikes can be made? See, I thought that question was so important I had to ask it twice. How many bikes can be made? What? Can you have half a bike? Okay. You can have an unbuilt bike. You're not going to be able to have half a bike because it's not going to move anywhere.
1 bike and a unicycle.
Okay, we have 1 bike and a unicycle, which means we only have 1 bike. Okay. What does that mean as far as the equation? What did you guys already go through and process and think about and do in your head in that process? Okay. You went through and processed 3 wheels, 2 frames, did all this calculation inside your head. What was that calculation? 3 wheels, 1 bike, 2 wheels. This says I can get how many bikes? 1.5 bikes. Can I have half a bike? No, so really I can only get 1 bike. And then the other one, I've got 2 frames, bikes, 1. Says I can get 2 bikes. How come none of you said 2 bikes? I look at the calculation, it says 2 bikes. I don't have that extra wheel. What you have already gone through and processed is said that I am limited by the number of wheels. I can't make a complete second bike. Even though I have the frame to build it, I can't make that second bike because I don't have enough wheels to process it. Which means I only end up with, if we could argue it, 1.5 bikes. Okay. This also means that wheels limited the reaction, limited my ability to make bicycles. I have now just discovered the limiting reactant. Okay? That's the limiting reactant concept. We look at how many things were possible, and we picked the smaller number. Okay? That's going to be the controlling feature in our overall reaction. Kind of makes sense? Oh, please don't lose connection. So we can do it again. You're making grilled cheeses. You need 1 slice of cheese, 2 slices of bread to make 1 sandwich. So we got a nice little equation that we could convert that to. 1 cheese plus 2 bread equals 1 sandwich. You have 5 slices of cheese and 8 slices of bread. How many sandwiches can you make? Numbers are starting to become a little bit more difficult. How many sandwiches can you make? Yes, Ivy. 4 sandwiches, which is limited based on what? The slices of bread. Okay, so our limiting reactant in this case is our bread. Okay. All we're trying to do is see what that equation means. We are converting the text into an equation so that we can then interpret what's happening. How many of you like word equations in math? Those stupid, lovely little word equations. Sally's taller than Jerry. Jerry's taller than Sally. What time does the train arrive to Milwaukee? Okay. That's chemistry. We're looking at all of these facts randomly combined, or what appears to be randomly combined, and you have to kind of whittle your way through and organize them in some fashion that makes sense. Ultimately, you're being told to organize them in the fashion that makes sense to me. I wouldn't go as far as smarter than you. Okay? Because that's how I understood it. Are there other ways to understand the material? Yes, absolutely. This is why you can talk to other people and see how they process it. Okay? But all you are trying to do is organize that information so that you can interpret it as quickly as possible. 2 moles of sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. How many moles of sodium hydrogen carbonate are produced? So we just complete right turn away from, or U-turn maybe, away from grilled cheeses and bicycles to now going straight into a complex equation. Set up some work. This one is significantly more difficult than the others, because in the others we only had 2 reactants. We now have 3 reactants here to take into consideration. So set up the work, prove to yourself that that's what's happening. If you got questions, raise your hand, I'll come to you. Moles of sodium carbonate, moles of CO2, and moles of water into the same unit so that you can compare them. At this point, you're comparing completely different things. Okay, so a question then arises, well, what unit should you make them all equal to? Does it matter? Ultimately not. You can make them any unit you want as long as they are all the same unit and you have the ability to do that conversion. My standard approach is to convert them all into the product, what I'm trying to obtain. The reason being is that after we determine the limiting reactant, what we'll then move into would be the concept of a percent yield. How much product did I make? Well, in a percent yield, it's the actual yield over the theoretical yield. In both cases, it's the actual yield of product over the theoretical yield of product. So if I'm going to need a product amount at the end of all this work, I might as well directly convert into the product unit. If I convert into any other unit, I'm only providing myself more work further on down the road. Okay? So, I start with moles of sodium carbonate. I want moles of sodium hydrogen carbonate. How do I convert that unit? How do I convert from one substance to another substance? Ratios found in the balanced equation, which theoretically is balanced. Good. Okay. So we're now looking at a balanced equation, so I can go through and use that information to do this conversion. Are moles of sodium carbonate the same as the moles of sodium hydrogen carbonate? No. So my units need to cancel. I'll put on the bottom moles of sodium carbonate, and on the top, moles of sodium hydrogen carbonate. What number needs to show up in front of each of those? Okay, why 2 over 1?
Because 1 mole of sodium carbonate is a recipe to make the 2 moles of sodium hydrogen carbonate.
We look to our balance equation. The number that shows up in front of sodium hydrogen carbonate is 2. The number that shows up in front of sodium carbonate is 1. This means that if I look at just the sodium carbonate, how much sodium hydrogen carbonate can I make? I can make 4 moles of it. That's all that means. Does this take into consideration how much CO2 is present? No. All it took into consideration was the sodium carbonate. It says nothing about any of the other reagents. So to do this calculation, what I am assuming is that the other reagents are there in excess and I don't need to worry about them. We have to make that assumption. If you don't make that assumption, that makes your calculations virtually impossible to do. Okay. So we now have to interpret what happens with our CO2. Okay, so now what I'll do is shift focus to looking at just the moles of CO2 provided. Is moles of CO2 the same thing as moles of sodium hydrogen carbonate? No, so what I have to do? I do a conversion. Moles of CO2 need to be on the bottom. Why? So it can cancel the units. Moles of sodium hydrogen carbonate needs to be on top. Why do I want sodium hydrogen carbonate? It's our product, so that's going to end up being my end goal anyway. And in the previous conversion, what did I end up with? Moles of sodium hydrogen carbonate. Once I do this calculation, I can now compare those numbers. What number needs to show up in front of moles of CO2? 1. Why? From the balanced equation. Moles of sodium hydrogen carbonate? 2. The result? 2 moles sodium hydrogen carbonate can be produced from 1 mole of CO2. We now have 2 numbers that we can compare. So let's ignore water for the moment. What is the maximum amount of sodium hydrogen carbonate I can make? 2. I cannot physically make 4 because I've run out of CO2. I've only got enough CO2 to make 2 moles. To make that next 2, I literally do not have enough CO2. I do not have enough wheels, or I do not have enough frames to continue to make. Okay? So what you could do is now put a line through your 4. Cross it out. Why? Because you don't want to use that number anymore. You've already proven that the next one down is the more relevant number to look at. Okay. Is our reaction with just 2 reactants? Nope, we have another one. So we have to interpret our water. Moles of H2O, what shows up on top? NaHCO3, that's a nice way to put it. Labeling all the letters out, that works. What numbers need to show up in front of each of those moles? The coefficients from the balanced equation, which happens to be 2 and 1. And we'd end up with, again, 4 moles of sodium hydrogen carbonate. What is the maximum amount of sodium hydrogen carbonate I can produce? 2 moles. Okay. What does that mean when we go through and look at these calculations? 2/3 of the work that you did gave you a number that was wrong. Okay? Did you still need to do those calculations? Yes. So they aren't completely useless. It's just giving you a number that is wrong. Okay? So when you go through and calculate a limiting reagent or determining limiting reagent things, you have to go through and look at every single reagent and convert them all over to products theoretically and see what your smallest amount is. Once you have that information, you can say, okay, there we go. That is now my limiting reagent. Okay. So let's draw the conclusion on that. Which of our reagents is the limiting reagent? CO2. Okay. If we wanted to get really obnoxious, i.e. 151, we could then say how much water was in excess. Ooh. Okay. How do we figure out how much water was in excess? Okay. We would go through and say, well, 2 moles of sodium hydrogen carbonate are produced. How much water is necessary to make 2 moles of sodium hydrogen carbonate? You go through and do your conversion. You should end up with 1. Okay. We start with 2 moles of water, which means 1 mole is in excess. That involves a sequence of extra calculations that is not strictly necessary for this class, letting you be aware of what you could end up being asked to do in a future chemistry class. Questions in this process? Okay. Percent yields allows us to normalize or standardize our results. So in that previous reaction, what we just calculated what was theoretically possible if all of the CO2 was converted into sodium hydrogen carbonate. What did we end up with for our theoretical yield? We said how many moles of sodium hydrogen carbonate? Your memory's not as bad as mine. Or you're really confident in making up answers. We made 2 moles of sodium hydrogen carbonate theoretically. When you go into the lab, does everything work perfectly? No. So when we go into the lab and run this experiment, we may actually notice that I get, as an actual yield, let's say 5 grams sodium hydrogen carbonate. How can I now normalize that 5 grams of sodium hydrogen carbonate? Because if you go through and do 5 grams, make 5 grams, and I go through and I make 500 grams, who did it better? Depends how much you should have expected. If you should have expected 5 grams and I should have expected 50,000 grams, I think you did a better job than I did. Okay? We have to normalize. Okay? In that normalization process, that is our percent yield. And when we go through and do that, the units must cancel. Your percent yield is unitless. How would I calculate it with these numbers? What was the actual yield? 5 grams. What was the theoretical yield? So the gut instinct might be to just do 5 divided by 2 times 100. And you're going to end up with this really big number. And I'm seeing some violent shaking of heads. Good, I like that. Would we have no units at the end of this calculation? No, we would have grams per mole. That is not unitless. To finish this calculation, what would I have to do? I have to either convert grams to moles or moles to grams. Does it matter which one? No. I've had students vehemently disagree with me on this, that it is shorter to do it one way versus the other. It's the exact same calculation. There is no difference. Okay? If I convert grams to moles, I end up dividing by the molar mass. To convert moles to grams, what do? Multiply by the molar mass. Exact same calculations. Okay? So let's fix this. I have no idea what that actually converted out to, and I didn't really feel like calculating it. Let's say you got 0.5 moles of sodium hydrogen carbonate. Punch it in the calculator, 0.5 divided by 2, and you've got your answer. Done. What would we expect for percent yields? Are there numbers that you'd be like, whoa, it shouldn't be that? That's wrong. Over 100 doesn't really make any sense. Okay. Why? One of our initial laws was the first law, we can't create or destroy matter. To get over 100%, we had to create matter. So we should never obtain a value over 100%. Does that mean it is impossible to do? No, it just means you're missing or you're making an assumption incorrectly. There's something else contributing to that weight. Okay? There's another number that should never show up in here. This one actually should legitimately never, ever, ever show up.
100%.
Nope. 100%. You just did a really awesome job, though you probably screwed something up. But 0%, okay, that will happen plenty of times. You will fail the experiment. You don't produce any product. Your yield, by definition, is 0. You can get 0%. That happens. Negative. You should never get a negative percent yield. That makes no sense. If you got a negative yield, you did a calculation error. That's not an experimental error. You legitimately messed something up within your calculations. Okay? There are only two numbers that go into this, an actual yield and a theoretical yield. Okay? Which means there are really only two possible multiple choice answers. Actual divided by theoretical and theoretical divided by actual. Your multiple choice answers, there are 5. We've only covered the base on 2. How could I possibly ask any or provide any other answers that would be even remotely possible? Okay, ooh, I didn't think of that. Sig figs, we could drop sig figs into it. Okay, that would be irritating, but we could do that. Okay. Another irritating possibility to it is that we add a third number in the question. That third number is not the actual, it's not the theoretical, it's some random other number. Okay? The experiment happened on the 4th day of the week. Someone's not reading the question very carefully, what do? 4 divided by the actual yield. 4 divided by the theoretical yield. I now have all my multiple choice answers. So when you look at a percent yield question, you need to be very careful with the numbers listed, because there won't be just 2 numbers, there'll be 3, maybe even 4. What 2 numbers do you need to calculate a percent yield? The actual yield, which should be your product, and the theoretical yield. To get the theoretical yield, you technically had to do a calculation. So the theoretical yield is also referred to as the calculated yield. You need those 2 numbers and those 2 numbers alone. Everything else, completely meaningless. You just take actual divided by theoretical, and you're done. Question? Okay. We're good with that. So limiting reactant / percent yield. This is kind of the end goal of what you get out of all this material. We move into the lab, we run an experiment, and then we have to predict how well we did at it. So a 50.6 gram sample of magnesium hydroxide is reacted with a 45.0 grams of hydrochloric acid. At the end of a reaction, a chemist recorded a dry mass of 60.0 grams, of magnesium chloride. What was the percent yield? Let's just start real simply here. Percent yield. How do you calculate the percent yield? Actual over theoretical. Are we given any of those numbers? Yeah, we actually are. We're given magnesium chloride, which is the product. How do you know that's the product? It says what we obtained at the end of the experiment. Okay, so that is one way to do it, reading the question very critically to say that's what we obtained. Okay, I will accept that. 60.0 grams of magnesium chloride divided by our theoretical yield. How much magnesium chloride should we theoretically have made? 95.6 grams. What you did was added the mass of magnesium hydroxide with the mass of hydrochloric acid to make your product. That would be a perfectly valid approach if this was a combination reaction. Magnesium hydroxide plus HCl goes to make magnesium chloride. So those are the only two things we've told you. Is this equation balanced? Nope. What are we missing? Water. HOH. Is this a combination reaction? No. It's a double replacement. The 90.6, the totaling of your reactants, is the total mass of the products. When you go through to calculate your theoretical yield, what do we want the mass of? Magnesium chloride. Do I want the mass of water? No. Is 90.6 the theoretical yield of magnesium chloride? No. It is the yield of magnesium chloride and water. Is the theoretical yield given to you? No. You have to calculate it. Doing what? From a balanced equation using stoichiometry. Doing the limiting reactant concept. This question is a beast as far as length. How many of you want to do this as a quiz? Good, I didn't really want to do it as a quiz either. Okay. To answer this question, all of those other questions must be answered first. Okay. What is the formula for magnesium chloride? The formula for hydrochloric acid? What type of reaction occurred? What were the products? What's your balanced equation? What's the maximum yield of magnesium hydroxide was your limiting reactant? What if it was hydrochloric acid? Which is the limiting reactant? Once you know what the limiting reactant is, you now know the theoretical yield. The actual yield was given to you in the equation. You can then calculate the percent yield. If you can do this question, you can do everything that we've possibly talked about within the last 2 exams. Okay? Requires a lot of thought and a lot of processing. It is something that in a future general chemistry class you would expect it to be able to do on an exam at least once, maybe twice. Okay? In addition to all sorts of other questions. Beginning to end, that should be under 10 minutes to solve that entire question. Okay? Probably under 5. Okay? Just to give you an idea of what's happening within it. That's the end goal of all of these calculations. And I have every faith that you can go through and do this. The issue is that you aren't breaking down into the individual steps. You aren't trying to make it smaller, you're trying to jump to the answer. Make every step as small as possible. Okay? Questions?
Will that be on the final?
No. Okay. The final does not include a question like this. It will include percent yield, but it will include it like we just said. Your actual yield is this, your theoretical yield is this, and random number. Do your calculation. Okay? Questions about that? Don't look so depressed. That's fun stuff. Last part of chapter 8 talks about empirical formulas. It is the fully reduced whole number ratio of elements within a compound. Okay? So if we looked at our formula for sodium chloride, what is our formula for sodium chloride? Thank you. Formula for magnesium chloride. MgCl2. Okay. How do we know our formula for sodium chloride doesn't have any subscript numbers? Kind of except periodic table. What about periodic table lets you know that? The charge on sodium is +1, the charge on chloride, -1. That formula is balanced. How do we know MgCl2 has the 2? Charge on chloride is a -1. Charge on magnesium is +2. We need 2 chlorides to balance. When we look at ionic compounds, they're kind of boring. The empirical formula is given for ionic compounds. We don't write this as Na2Cl2. Okay. That still gives us the proper balancing between those, but it's not the fully reduced formula. Okay, so in our empirical formulas, ionic compounds are always in their empirical formula. But what happens when we move to a molecular compound? Let's see, did I actually provide a structure? I did not, so I'm going to have to draw it. Anybody know the formula for benzene? No budding organic chemists, huh? Oops, made it too big. This is our formula for benzene. If you go through and check that, all our octets are satisfied. We're all nice and happy. What is our structure for benzene? What would our formula be? How many carbons are there? How many hydrogens are there? So the formula for benzene is C6H6. Why is it not written just CH? Because if we look at sodium chloride and magnesium chloride, we wrote them only as ones. Why is sodium chloride not, say, Na6Cl6? It's a good question. What is the difference between sodium chloride and benzene? Sodium chloride is, ooh, it sounded like someone was about to say it. It's an ionic compound. C6H6 is covalent or molecular, which means different rule sets. Okay. Ionic compounds will always be in their empirical formula. Molecular compounds, depending on what you are looking at, you may write more appropriately as the actual formula. And that's because within those covalent bonds, benzene does not link to another benzene molecule like sodium chloride does. Okay. Why? It's not charged. So it doesn't have that same rigid structure that we get in our ionic compounds. Writing the formula for benzene as CH is horribly inaccurate. Because if you look at CH, you would say there's 1 carbon and 1 hydrogen. Well, in the structure for benzene, that's not the case. There are 6 carbons, 6 hydrogens, and they are all covalently bound in that fashion. There is no linkage between those individual molecules, which means we have a different understanding of our formulas. We have to interpret them slightly differently. So within our empirical formulas, we will always look at our whole number ratios. In benzene, if you were asked for the empirical formula, it's just CH. You just reduce the numbers down as small as they can go. Okay? Why do we talk about empirical formulas? This comes from chemical composition. So if I went out into the wilderness, found some random plant, crushed it up, rubbed it on some wounds, and it healed the wound. Okay? Well, that's cool. Something in that plant is healing the wound. There's probably a bunch of stuff in that plant that's not healing the wound. So what would I do as a pharmacist or a researcher? I want to extract whatever that healing property is, get it out so that I can just smear that on the wound and not all the other junk that came with the plant. Okay? To do that, I'm going to have to come up with some kind of processing, some interpretation of the individual molecules within it, and probably end up doing something known as chemical composition. Whoops. A chemical composition analysis. So within that, what I can go through and do is break the compound down and evaluate the mass of each of the individual atoms or the individual element types within it, and then I can convert that back into an empirical formula. Okay, so if I take an unknown compound of radium oxide and I find that it contains 0.726 moles of radium and 12.3 grams of oxygen, what is the empirical formula? Okay, well, what does our formula show us? If I give you NaCl, what does that formula tell you? There's one sodium atom and one chloride. The numbers of them. Okay. What do moles tell you? A very large number of them. So if I give you 1 mole of sodium chloride, how many moles of sodium are there? 1 mole. Okay. It's just a very large number, but as long as I'm talking about moles, it's the same. 1 dozen sodium chlorides means how many dozen sodiums? If I give you 12 of these, how many sodiums are in that? 12. How many chlorides are in that? 12. So when we look at our formula, it's really telling us the number of moles within an individual compound. So if I go, what I want to know is what number goes here and what number goes here. Well, we just said it's the moles. So I've given the moles of radium 0.726. Okay. Anybody going, well, that looks ugly? Yeah, good. You should be. We want the whole number ratio within our formula. Not these weird decimal things. We want a whole number. So 0.726 is not a whole number. So that becomes problematic. What would we put for our oxygen? What number am I given for oxygen? 12.3 grams. What unit shows up in my formula? The number, or moles. Is grams moles? No, I got to convert it. So 12.3 grams of oxygen. How do I convert that into moles? Just because you said that, I appreciate that honesty there. It is not either divide or multiply by the molar mass. No, you're going based off of a formula. Do not go based off of a formula. What unit do we want? Moles of oxygen, which means moles of oxygen needs to show up where? What unit needs to show up down below? Grams of oxygen. What is the conversion factor between grams of oxygen and moles of oxygen? There are 16 grams and 1 mole of oxygen. What number shows up in front of grams? 16. What number shows up in front of moles? 1. Okay. The issue of saying you either multiply or divide, you're now saying it's a coin toss. You don't know. You do know. Follow the units. That's why the units are there. Okay. You can solve any question if you follow the units. If we go through and do that calculation, what do we end up with? Five? Something? So we've got a number that we can put in there. We can now say that our formula is that. How many people like that formula? How many people don't like that formula? Okay, that's a little better. Just checking. Okay. We want our smallest whole number ratio. How can we get the smallest whole number ratio? What were you going to ask?
I was going to ask about sig figs.
We'll worry about sig figs here in a second. How do we get the smallest whole number ratio between these two species?
You add more radiums and oxygen.
So we could start adding more radiums and oxygens until it balances out. That's going to be a bit tedious. No. How do I make 0.726 a whole number? What do I have to do? I could multiply by a weird number. There's an easier way. What's that? No, not rounding. We have to multiply or divide. It's a lot easier than you think. How can I make it a whole number? Divide it by itself. If you square it, it's not going to get a whole number either. If I divide 0.726 by 0.726, what does it become? 1. So I would get Ra1. What should I now do to the oxygen?
Divided by 7.726.
I will end up doing the same thing in little air quotes. The same thing meaning divide by 0.726. Why do I not divide by 0.7687? What we're trying to do is do the same thing to both. If I divide one side by 2, what do I have to do to the other side? Divide by 2. If I divide one side by 0.726, what do I have to do to the other side? Divide by 0.726. What number do I get? And then a lot of numbers. Okay. Still haven't fixed my whole number issue. Now what can you do? Here's your first suggestion. Round. And you end up with your formula, your empirical formula, as Rao. Get it? Rao. Never mind. Radium oxide, RaO. This gives us some information about our compound. That is the whole point of empirical formulas. Does it tell us what our final structure is? No. But it gets us a little bit of information about it. Can we do this with covalent compounds? Absolutely. Same process. If you have carbon and hydrogen in the structure, you go through, convert them into moles, put it into a formula, divide by the smallest whole number, or the smallest number, and you've got your formula.
Was that already given to us by the formula?
So that's assuming you know the charges. That works for an ionic compound. It does not work for a covalent compound. So I picked an ionic compound because we now have a quick way of checking. Okay. So you will have to go through this work to figure out your empirical formula for all covalent compounds. I want to go back. Yeah, no, that works. So if we look at our empirical formulas, our steps, convert all of your units into moles for each element. Okay, you will likely be going from grams to moles. You'll go through grams to moles using the molar mass coming from your periodic table. Okay. To get your percent composition, okay, sometimes you're told that it is 12% copper or carbon and 92% hydrogen. Well, that's not a gram amount. How can you convert that into moles? Assume you have a 100-gram sample. If you have a 100-gram sample, that means 12 grams of it are carbon. The other, I said 90. I can't do math. 88 grams are hydrogen. Okay. So the percent composition, just assume 100 grams and figure it all out as far as your numbers go. Once you've got the mole amounts, divide your mole amounts by the smallest mole. Now you can round or multiply values by fractions to scale it up higher. Okay. Under most circumstances, when you divide by the smallest whole number, you will end up, or smallest mole value, you will end up with whole numbers through the whole thing. Your empirical is then your element by the whole number, element, whole number, element, whole number, all the way through. The next step, how do you then get the molecular formula? Okay. Well, in the molecular formula, what you will do is first determine the mass of your empirical formula. So let's say your empirical formula was CH. What is the molar mass for the empirical formula CH? Good shifting to the periodic table. I like that. 13. The mass of carbon is 12. The mass of hydrogen is 1. Add it up, you now have the molar mass for your empirical formula. What you will now do is divide the molar mass, the molecular molar mass, by the empirical molar mass. Well, where did you get the molecular molar mass? It's given to you. Okay. When you do that division, you will now have a whole number. Okay. All you've got to do is now multiply your whole number, your empirical whole numbers, by the whole number that came out of your calculation. Okay. So let's take a look at this one. Yep, let's go beginning to end on this. An unknown sample was found. Yeah, we're going to have to go to that. Unknown sample was found to be composed of 24 grams of carbon, 2 grams of hydrogen via elemental analysis. What is the compound's empirical formula? Our first step is to do what? Convert to moles. Hey, that's kind of a funny thing. We did all our conversions. What did I say was your first step always? Oh, convert to moles. Look at that. Still holding true. 24 grams of what? Carbon. How do I convert that into moles? What? 12 grams is 1 mole. Hey, look at that. You didn't even look at the periodic table. How'd you know that number? If you've done enough calculations, you will start to memorize the numbers. Okay. What's 24 divided by 12? 2 moles of carbon. And then we had 2 grams of hydrogen. And we end up with 2 divided by 1.01. You can just approximate. Come on now. 2 moles, whoops. Oh, I see what you did. Yeah, or what I did. Like how I blamed you there for a second? What is our empirical formula? We could say it's C2H2, but that is not our empirical formula. Our empirical formula is the smallest whole number ratio, which means CH. Hey, look at that. I would have thought that maybe I picked an example that I'd already talked a bunch about. We now have an empirical formula, CH. Okay. That's how we go through and process it. Questions? Let's do the molecular formula. This same amount of sample was found to have a molecular mass of 78 grams per mole. What is the compound's molecular formula? What did we say the empirical formula was? CH. And we talked about the steps for figuring out our molecular formula. We need to figure out the molar mass for our empirical formula, which we already said was, Stephen?
13.
12.01 grams per mole from our carbon, plus our 1.01 grams per mole for our hydrogen, and we end up with 13 grams per mole for our empirical formula. Our next step is we take the molecular molar mass, which was 78. So this is another step. Let's go ahead and change the color. And I will then divide that by 13. Carry the 1, divide by the 4, and we end up with 6. Our last step was what? Take our empirical formula and we will now multiply everything by the whole number we just got, and we end up with C6, did you say 10? C6. That works. C6H6, look at that, full circle. Almost literally, because benzene is the shape of a circle. Hey, yes. Okay. There's our molecular, or our empirical to molecular formula. By understanding what our formulas mean, it's now just a process of putting that information in and interpreting it out. Okay. Where we will pick up with on whatever that next day is, Thursday, is we're going to look at solution chemistry, and ultimately probably my favorite lecture, which seems to be everybody else's least favorite, intermolecular forces, and predicting all sorts of fun, awesome things that can come from just understanding electronegativity and intermolecular forces.